Okay, so I was given the assignment of this one. I didn't come up with the first part of the titles. I'm supposed to talk about seismic noise and DAS. It's a biased one in two senses. The first one is that usually when I think about the work we are doing at Caltech Seismic Lab for the DAS work, we have a very specific science questions in mind, and we use whatever tool we need for that problem. Like if we're imaging a volcano, we use ambient noise, earthquake, active source. But today I'm going to take the opportunity to think it from a technical perspective. So not too much on the science question, but like how DAS has been really helping us to do ambient noise seismology better. So it's a little bit more technical that way. And another reason it's biased is I choose to focus on work from my own group, mostly not because there's a lot of other good work out there, but because this work have, I know the details. I can talk in depth about some of their challenges and opportunities. So I'm be able to answer your questions better. So feel free to interrupt me with any questions. Okay, since this is a school, let me start with some basics. So what is the distributed acoustic sensing, DAS? Well, DAS is this technology that will turn a fiber optic cable into dense seismic arrays. So the way it works, if you have a cable buried underground, usually this cable already deployed for telecommunication purpose. You connect this DAS interrogation unit to one end of it, and it will turn every meter or every 10 meters of the cable into a sensor. It works by sending a laser pulse to the cable, and the cable is designed for transmit light, so it's very efficient at doing that. But at the same time, when they make the fiber, there's always tiny defects, imperfections in their cable. So here illustrated as little dots. So this might be small density perturbations within the glass. And then when the light is traveling in it, they're actually causing some minor amount of backscattering, very, very small amount, really backscattering. This interrogator sends that pulse and it will start to listen. It will listen for the echoes coming back. So one pulse in, you get a bunch of echo coming back. And then a moment later, it will send another pulse and listen to the echo again. Well, if everything is exactly the same along the cable, then the two echoes should be exactly the same. But if you look into details, they are not the same because the fiber has been perturbed between the two parts. Maybe it's due to earthquake shaking, seismic shaking. And we are able to look at the perturbation of those pulses and figure out what has been happening on that section. So you send the pulse in, you listen to the echoes. Based on the two-way travel time, you also know where this perturbation is happening. So now you can look at this backscattering along different sections of the cable and figure out, turn this into a dense seismic array. Go into a little bit more details here. This is actually a numerical simulation of the light propagation in the cable. So here I'm simulating a cable that's 20 kilometers long, right? So I send the pulse in, I listen to the echoes based on the two-way travel time. I can translate the time series of echoes I hear into distance along the cable. So you can see there is this general decay just because earlier in the section, the light travel was a bit shorter, so you hear stronger echoes, and they're decaying as a function of distance. This decay is the reason why DAS usually works on cables less than 100 kilometer distance. Going beyond that, it's getting hard. You need to have some special technology to make it work. Okay, so now I'm sending one pulse in, I get a reference echo back, that's the blue one. And then after a moment, some perturbation. Here I'm applying a synthetic perturbation to this section of the cable. And now I look at it again, now I can see the one after perturbation is slightly different between the two. Here, what I'm plotting is backscatter power, so how much light is coming back. You can also look at the phase information of the backscattered wave. So in the early days of DAS, people were actually using amplitude information only. Phase was a bit harder, so later it's called quantitative, where you can do the phase information. Before that, it's more like a qualitative. So you know something is happening at a section of cable, you don't know exactly what's happening. Right? That's useful still if you are interested in intrusion detection. So you can get a cable around an airport, for example. If someone is trying to come in, you don't know, you need to know exactly what's happening. You know something is happening along that section of the cable. But later, it becomes quantitative. You can measure the phase information. So now this is like the difference between the two. That's the kind of intensity based. If you zoom in into that section here, this is the power distribution. And you can now look at the phase difference between the two. Before that point of perturbation, there's no phase difference between the two. And after that point, you get this kind of slope here. And that slope, in this particular case, I was stretching that section of cable just by tiny amount. So now you can see a phase difference, right? But you say, why this have steps? Okay, so at the steps, clearly I'm not making good measurement. You're only making good measurement at the slope part. It turns out if you look at the backscattered signal here, you see there are points along the cable, very little energy seems to be backscattered. Well, you have all the defects along the cable, why some section doesn't seem to give you backscattering. This is because we are looking at a gauge length, so-called, right? So you're averaging over a certain length of the cable. You send the parts in, every little defect within that 10 meter are scattering some energy back. Everyone have a random phase and a random amplitude. So what you observe is actually a summation of all the backscattering from all the defects in that section. And it's a random walk process. There is a good chance that you get some reasonable amplitude, but by chance, sometimes you're back to zero. They all interfere so that nothing is coming back. At those points, you cannot make a good measurement. So all those points near zero is called a fading point. At the fading point, you cannot make a reasonable estimate of the phase information, right? So I was talking with some people yesterday about this kind of problem. So their DAS manufacturers spend a lot of time try to reduce the fading point and improve how they can measure the phase information. As you can also see, if you use a relatively shorter gauge length, you may get more noise in their measurement. If you want a stable measurement, you may want to have a longer gauge length, right? But that also reduces your spatial resolution. Yeah. So this is some basics of how DAS works. So of course, one of the biggest strengths of DAS is you are turning an existing cable into sensors. So as long as you put this DAS unit in and you power it and you have data telemetry, suddenly you have a dense array that is permanent and is continuously running. I'm going to argue that this is the two major reasons why DAS is such a great opportunity for ambient noise seismology. I want to put this development into this context here, kind of the history of seismic instrumentation. Horizontal axis here is quantity. Essentially, it's something like the number of sensors you have. Vertical axis is even more qualitative, like quality of the sensors. Okay, there are many factors: sensitivity, noise level, dynamic range. I'm kind of lump them together. I would say the last 100 years of seismology, most of the time we are going along this path here. We're trying to go from a single low-quality sensor to many, many very high-quality sensors. Right? I'm using the Southern California network as an example. It's a very large, high dynamic range, high sensitivity network. But I think starting 10, 20 years ago, probably on the order of 20 years ago, we start to see a reverse of this trend. It's hard to keep going in that direction. We have a really sensitive instrumentations, and they're very expensive, not only just the hardware, but how much effort it takes to go deploy it. I'm amazed by this work that Florian was doing, right, to put a dense array and maintain it for a couple of years. It's hard to do to keep going in that direction if it's conventional broadband network. So what we have seen is going down in this direction. You try to have lower quality sensors, but you try to have orders of magnitude more of them. Okay? Some good examples of this is nodal seismic sensors, very easy to deploy. Another end-member example is using MEM sensors, either as a cheap, what do we call it, a community seismic kind of sensor, or just using people's phones, giving people an app, so your phone's sensor can be used for that purpose. In this context, DAS is really going further towards the right direction. As you will see later in the talk, I believe DAS data quality is kind of comparable to the nodes, okay, in certain frequency band. So it's comparable to that, but we are able to get another 2 order magnitude of sensors with relatively little effort. So this has been benefiting a lot of different kind of research. A lot of my research is on earthquake-based tomography, imaging rupture process, looking at glaciers and other environmental issues. But today I'm just going to give the focus on the technical review and how does this affect noise seismology. I would argue that this is the great opportunity for ambient noise seismology because of the scalability of the method, the kind of sensor density you have, and the fact that it's continuously operating. So, up to now in this week, I have been learning so much from the other lectures and the posters. I see a few major kind of applications been showing up in their school so far. Ambient noise tomography or imaging, for look at structures. There's a lot of emphasis on characterizing the fault behavior, either the fault structures or the changes or other activities on the fault. Temperature change seems to be a big thing that's happening at the moment, either due to tectonic process or environmental process. And also there's a lot of interest in how the ambient noise is being generated. So I'm going to structure my talk to show some examples from my own group, how DAS has been helping in each one of these categories. Let's start with the ambient noise tomography. This is actually the most straightforward one. So I'm going to give you one example to demonstrate that. So in 2019, when we were just starting for working on DAS for 1 or 2 years, the Ridgecrest earthquake happened. And after this is the aftershocks of the earthquake, the 6.4 followed by a magnitude 7.1. We know there's going to be tons of aftershocks, so we quickly contacted one of the telecom company in the region and get access to the cable. So we put a DAS unit in the town of Ridgecrest, convert this 10-kilometer DAS into a seismic array. This was the largest range at the time. So most of the DAS at the time is 10, 20-kilometer range. Now it's longer. So it's every 8 meters. So we have 1,250 sensors. The array was actually deployed like 5 days after the earthquake. So it's still considered a rapid response. In the same time, when USGS was trying to deploy broadband sensors in the same region to capture aftershocks, they had even more trouble to getting permit, getting the instrument and people to go, right? Yahuda was very fast and it was able to put a lot of nodal sensors, right, to put into that area. So in this case, because this is owned by the telecom company, once we get access, we were able to send a 2-people team and then get this done in about half a day. And then this array was actually still running even today. It's our longest running DAS for the moment. So this is actually what it looks like when you do field work using DAS. You're not really in the field digging anymore. So this is one of the so-called nodes. So the cables running, along the street, eventually go to in this room. Inside of the room, there's all this telecom equipment, which basically amplify the signal, distribute their telecom signal. What we do, we go in there, take this DAS box, plug into their cable, and that's it. It's done, right? And we set up the internet so we can get the data, look at the data remotely. This is one of the first, yeah, you have some choice of that, but basically what you're doing is you are taking an average phase information from the reflection in that range. If you take a longer, it's a more stable measurement, it's lower resolution. Exactly, yeah. The way you do it is, of course, you listen to all the echoes coming back, the backscattering, and you window it to make that measurement. So you can choose your length of how you want to do it. But for most DAS machines these days, you have to set it up in real time. So you don't get to keep the raw data to do post-processing because that optic data is very large volume. Okay. So this is one of the very first DAS measure. Feel free to ask questions. Thanks, Alex. Just feel free to interrupt me. I don't have 120 slides. Okay. So this is the 10-kilometer range here. Ridgecrest is this end. And now you can see the color is basically showing positive and negative strain rate. And this is where the earthquake P wave come in, where this is where the S wave come in, right? So this is like amazing at the time, right? Like when suddenly, if you show that like with that, you can really track the whole wave field. If you look at the individual sensors, of course you can identify P and S waves, but now with this array, you can see all this richness in the wave field. You can see all these later arrivals, at what speed they are propagating. You can see some of these arrivals that's propagating at a different speed, which I will come back to. But yeah. Oh, these are not fading point. When you deploy your telecom cable, you want to be prepared that something might go wrong one day, so you need to go service them. So they have this thing called manholes. The cable goes in there, they have a loop of cable in there. So if something is broken, they go there, cut it, and then redo it. But in the manholes, the section of cable is not touching the ground, so you're basically not getting much energy. So we mute them in this plot. By this kind of array, we were able to detect many more times earthquake than the conventional seismic array nearby using the Southern California network. So this is the cable. Now color shows you where you can detect more earthquakes, whereas red, we're detecting about 10 times more earthquakes. But most of this earthquake was actually very small, so not like the one I showed you earlier. Most of them are like this, right? So this again is distance and time here. This is the earthquake signal. And each one of these is one car driving by. So every car driving along the road, we can track the vibration of that car. So the slope of this is actually the speed of the cars. So we can tell exactly who is speeding in this case. But what's more interesting is you can see as the car is propagating, there are these kind of chevron structures around it. So these are actually, as the car driving, they are radiating radio waves from them because it's not exactly smooth. Right? So we actually can see all the propagating seismic noise in this case. So as you can imagine, when you do ambient noise correlation in this case, those traffic noise is actually your primary noise source. So it's actually an interesting setting. Come back to this ambient noise source distribution problem. You have a highway, your cable is next to it, your noise source is propagating back and forth along the same line. So in some sense, for this particular case, you only have noise source exactly at your stationary phase zone, right? Which is great for this purpose. But I also see in other examples in my own group in other urban settings, because you have a grid of road, sometimes that distribution can cause trouble to ambient noise correlations. So we are very lucky in this Ridgecrest case because it's a smaller town. This is basically the only busy road throughout town. Right, so that's their chevron structures. So this is what you get when you do ambient noise correlations, right? So this is after stacking the causal and acausal part. I'm taking this particular channel here, this is the distance. I'm taking this particular channel here, cross-correlate with the stations, channels on both ends. And you can see very beautiful propagating surface waves here. And you can actually see the two sides have very clear different slopes. So even without inversion, you know there's lateral variation. So now you can do the standard approach. I'm not going into details of those. You can take any section here. You can measure the slope of this for different frequency, and you are able to construct dispersion curves. And because for every section of the array, you can find a lot of virtual source for you to use. So you actually can give more realistic estimate of the uncertainty of this. So this error bar here is coming from many, many snapshots like this received by the same subarray along the cable. So this is the dispersion map. So now vertical axis here is a period. So color tells you the phase velocity. So now you can see the difference along different sections, and then we use pretty standard method to invert this into. Yeah. We do see some body waves. It's not always clear and usable. So far we have been kind of staying away from that. It seems that the body wave most clear if there is a particular noise source that gave a very strong body wave signals. Like there is a pumping station with a motor inside that seems to generate a lot of P waves, but only when you have a virtual source there, you get a very clear P. I think this may be one of the examples.
And what is you stopped here at 1 hertz, but you're
Yeah.
holding much higher frequency.
This is the period, yeah. So this is, so it's 1 to 10 hertz here. 1 to 10 hertz is actually the best band when we use traffic noise. Going lower than that, you can go a little bit lower, point maybe 3 hertz, 3 seconds. You can go a little bit higher, but on both ends it's getting worse. Yeah. So we can convert this now into a tomography model. So now you can see we are looking at this 8 kilometer area, depth down to 200 meters, and you can see, quite strong lateral variations in this area. This actually was making a lot of sense because we know that the ridge crest end was actually a dry lake. So like it's the lower point in the basin, right? So the sediment all get transported towards this end. That's where you have thicker and slower sediment here. I want to end this discussion example by talking about this anti-correlation here. So the blue line here is showing you derived from this model, the so-called VS30, right? Time average shear wave velocity in the top, which is, Fabric can correct me, but this is a pretty well used, parameter for geoengineering purpose or civil engineering purpose. So you can see the velocity is higher there and it drops here down to about 300. The red line here, which I don't have time to talk about, but it's from those earthquakes we have detected. We can look at from those earthquakes, what's the site amplification effect from the same cable by looking at the earthquakes. And we derived the site amplification factors here, right? And you can see they really have this very clear anti-correlation here, right? Two different things, but very clear anti-correlations. Yeah, I wish I have the slides. We have other ways to check the coupling effect. Checking coupling is usually not the best with local earthquake because you have all these other factors that could come in. But you could look at longer period waves from further away earthquakes and it will show that on average, there is no systematic variation. There is a very small local scale variation, but nothing at this scale. Yeah. Okay. Wow, yeah. Thinking the same way. Okay, great. So this really shows us in urban areas, if we can do this kind of tomography, we really can help with this engineering problems. So this is actually the only example I'm going to show about this immunotomography topic. We have been doing this in the oceans. We've been doing this on volcanoes. We've been doing this in Antarctica. But I think the key message here is already demonstrated. Because of this extremely high sensor density, you get a really much higher resolution images if that's your target, right? So it doesn't help too much with look at a very deep structure, but if you're interested in shallow structure, it's a very high resolution. And it's working where you have cables. So it could be onshore, but it could be offshore. So if as long as you have a cable, this is a much easier way to do that problem. Any further questions on tomography? Yeah. Okay. So we actually have tried quite a few nonlinear arrays. Sometimes it's actually like a box. The biggest theoretical challenge of that is when you have cable, okay, that is measuring length change of the cable because you are measuring the phase difference as the wave propagate. So if the wave is coming from the side, it's supposed to have zero sensitivity. Okay, so if you now have a nonlinear array, you say, oh, I only can use a linear sections to get a Rayleigh wave. Maybe the other part I can get love wave. Our experience was not that. We see Rayleigh wave on almost all geometries and a fairly little love waves, at least in these urban settings. We think there are two reasons. One is cars are good Rayleigh wave source. At least in this frequency band doesn't seem to be a good love wave source. I would think the wheel is, have sheer traction on the road, but we don't see a lot of the love wave. The second reason is the theoretical direction sensitivity of the cable doesn't consider the heterogeneity inside Earth. Okay, so it's, the waves coming in, very local heterogeneity near the cable can turn a Rayleigh wave signal have a tangential or a long strike string component, right? Even if it's coming parallel, wavefront parallel to the array, right? So I think yesterday, Michelle, one of your postdoc student, was showing this effect of heterogeneity. So this heterogeneity effect is not considered in the theoretical direction sensitivity, which is a cable in a homogeneous Howard space. Right?
This is a one-component seismometer.
Yes.
So how do you distinguish between A and live?
Really, yeah. So usually you can only distinguish them by their dispersion and velocity. Yeah. So on a single component, you cannot distinguish them. Love wave, we do. But what you see sometimes basically is a mixture of both. Yeah. Yeah, absolutely. Yeah. So there are cases when we try to calibrate their data rate, in some sense, the instrument response. We use earthquake that's propagating parallel, right? So you can get the pure radio wave or a P wave component of it. Yep. I think as a reason it is a single scattering. The reason is every time the scattering is very small compared to the incident wave. I think it's on the order of 10 to the minus 9 energy. So if you do a multiple scattering, it decays very quickly. I think people look into this. It's still manufactured to make the propagation really efficient. So it's fairly long, relatively long free length. So single scattering is a pretty good approximation. Yeah, but this is slightly outside my depth of understanding here. Okay, so now let me go to the second problem, specifically for fault detection and imaging. So we hear a nice talk from Yehuda and others about why we need to care about the fault, where are they, what the kind of structure they are. But this is not an easy job, right? Majority of the time, you rely on geologists go out there to see the faults. Now there are some better ways using satellite imaging, basically different compliance of the fault responding to external loading. You can look at the seismicity. Right, once you have high-resolution seismicity maps, you can see lineations, or fault zone waves can be very helpful. I want to show this one interesting example I saw on LA Times, why this is actually also a pretty practical issue. So in Hollywood, there was some billionaire was trying to build a high-rise building, and the CGS, California Geological Survey company, said, no, you cannot build here because there is a fault nearby. And so they draw the fault, where are the faults, and I think this the complex they're going to build. And the company said, no, you're wrong. They hired their own company, geophysics company, did a survey in the same region, said there's no fault cutting across here, right? Just showing you, especially in urban area where things are getting covered, getting modified, sometimes it's hard to get very accurate information about the fault structures. So how do we use that to help on this problem? So I'm going to stay using this Ridgecrest data array in quite a few examples. So this was the data array we were looking at. If you look at the best USGS map for this area, it shows that there may be these 3 potential faults here. Where they show things as red or maybe yellow is where they have some confidence with the geometry of the map. So they seem to be confident there's something to the north, but they don't think it's cutting here. This one here, if it's dashed, it's inferred. So something's north, something's south, they draw a straight line through it. So how does this thing show up in our DAS record? So I'm now going to show you the noise correlation profile one more time. So it's the same thing, except last time when I show you, I flipped the positive and negative side together, right? So I only care about the phase information. Now you see both the causal and the acausal part of this. So these were the waves we were using. Now I also changed the color scale so you can see the weaker arrivals. So now the direct arrival is very saturated. So now you see all these other details, right? So imagine usually if you have conventional sensors, you would take one pair, which would be one slice here, and this would be causal, acausal part of it. And then now you can see all these things happening in between. You would say, oh, spurious arrival, something's happening. But now you can really tell what's happening. You can actually track this back, see where it's happening, and it must be generated here. And in some cases, you actually can see these things keep going. On the other side, you can see similar behaviors. So in this case, this would be a noise correlation function. This is later in time, so this is a coda wave. You say, oh, that's a coda wave. But now with that, you can track it, how it's propagating. You know exactly where it's coming from, right? So with this information, we actually know these are actually faults. What's happening here is you have the surface wave, this is along the distance. You have seismic waves propagating if there is a fault zone structure. It will scatter the wave, so some waves keep propagating forward, but there's some amount of energy going backward. All the surface wave coming to this point will get scattered. So in some sense, it's now you have a secondary noise source, but it's a persistent, localized noise source. And in Michel and Shapiro's talk, it shows that if you have a homogeneous distribution, you get a perfect Green's function. But if you have this non-uniform distribution, persistent, localized source, you get this scatter effect and get these spurious arrivals. And those are the reason for that. We actually get into a little bit more detail here. We actually can identify, this is a synthetic simulation. We just run a finite difference and we do noise correlation on the synthetics. These are the direct arrivals. So that's if you have a noise source here propagating for the two stations, you get the direct wave. And then you could have a scatter point here. So there could be a true part of the Green's function, go to the scatter and come back. That gives you a coda wave. But you could also have a spurious arrival, which is the scattered wave come to that scatter point, come to this station, but then it correlate with the wave to the other station. And the travel time will be less than the direct arrival. Then that gives you the spurious arrivals. We actually can see this very well in the synthetics, right? So now we know this is happening. We can kind of compare that with the actual observation. Where we put the fault in, you can see you can generate that spurious arrivals. We have this understanding. Now we say, can we do this more quantitatively? Remember that I already showed you a very nice tomography model of this problem. So there's a scatter point sending wave in both directions. And now I know the propagation speed in all the sections. I can do a back propagation of the wave so that they will focus at where they exactly get scattered. And not, I'm not limited to only this strong spurious arrival. I can look at other spurious arrivals, see if they stack coherently in space. And that's what we did. For each frequency, we can do it. And then the color here shows you where you get strong secondary scatters. And on the map here is a USGS map of the fault. And you can see we have strong scattering here, strong scattering here, and strong scattering here. If I now pick on the maximum of this, these are the map you get. So these ones are exactly matching where they are, except I think this location is wrong. It should be a couple hundred meters towards the east, right? And then we actually can see the frequency dependence of that. So potentially, there are some deeping structures on the fault. When you go deeper, the location is a little bit different. We even try to explain the amplitude of the scattered wave. So given whatever velocity anomaly you have, you get a different strength of scattering. So we take a relatively simplified model, we take our tomography model, we stuck in this low velocity layer, it's very simplified, with a certain width and depth and velocity perturbation. Now we do a research, see when we can match the observed spurious arrivals. In the end, this is kind of the matching. In the end, we got some fault widths on the 35 meters. We think the velocity reduction within the layer is about 30%. Unfortunately, I think the depth constraint was the poorest because we only have a narrow frequency band. So most of this is a fairly shallow fault. But in some sense, that's also important because that means whatever this fault is, it has been active all the way to the surface, a fairly recently active fault, right? So hazard purpose, it might be pretty useful. So these are the kind of fitting we are doing as a functional frequency. We recently tried to look at some bigger fault. That was like a teeny tiny fault. Happens to be under our array. Yeah? Oh, very shallow dipping angles. Yeah, it could be hard. It could be hard. We didn't dive too much deeper than that. We know this is a fairly vertical fault. We see some offset, so that's consistent, but we haven't tried any shallow deeping fault. Yeah, good question. Okay, so we have another array. So Ridgecrest was here. The company was really happy about what we have been doing with their cables, so they said, use my other cables too. So we put another DAS array. By this time, we have a better DAS. You can take a 100 kilometer cable. So we take the cable to the south. And this is the Garlock fault, which is one of the major faults in California. And there is a section of the cable crossing the Garlock fault, so we did additional tomography here. So I'm going to go a little bit quicker on this one. But what we did was we did both ambient noise and active source. So we actually went out there, hammered the ground every 100 meter, every 10 meter actually, along the fault, try to image the very shallow structure. And then we use the ambient noise. This is ambient noise along the cable. Across the cable, you actually can see the big difference on the two sides of the fault to look at the slightly deeper structure. And then we realize ambient noise in this case only give you the top structure, so we use additional local earthquake travel times to constrain a little bit deeper what the fault geometry is like. One of the bigger questions was what Yehuda mentioned of the bimaterial contrast across the fault. And we want to know the contrast at the seismogenic depths, not only at the near surface depths. So I'm going to jump to the result here. This is the tomography for the very small section along the fault. This is where geologist is mapping the fault. You can clearly see there's this low velocity structure at the surface, but maybe more robustly is at a slightly larger depth. You can see this kind of step here. So if you look at this, you will say, yeah, the north, so north is towards the right, is where the fault is faster than the southern side. And that has some predictions, right, about the rupture process. And if you look at the travel time from earthquakes, you do see that our shallow model actually explains majority of the observed travel time. So most of the travel time anomaly from earthquake coming from below was explained by this very top layer structures. Okay.
Sorry, you have the one dimension.
Yeah.
The GR is 3D. So how does it impact your tomography planning? You have not the whole information.
I'm a very traditional seismologist. I need to learn from you. Yes, everything is 1D inversion and then compile them together. We sometimes consider the lateral smoothness that we expect from the problem and helps to do the problem a little bit better. But most of the time, it's a local assumption. Yeah.
How do you suppress all the environmental noise, like all the local noise? You're stacking over time?
I thought the noise is what we use for imaging, right?
But I mean, temporal changes, right? Daily, lots of things happen.
Oh, right. Stack over time is important to that. Yeah.
So you're stacking over time?
Yeah.
1 day?
Usually we stack 7 days at least. Because we worry about the weekly traffic pattern. Like weekend and weekday, people drive differently. You will actually see that. We actually can see that difference. Okay, so this is interesting. So for the shallow part, we get a pretty good idea about the model. But you say, okay, the observed one versus the predicted one, there is still a difference. Especially there is a systematic offset on the two sides. Okay, where is that coming from? Does that tell us something about the fault contrast at larger depths? Well, if we zoom out a little bit, this feature is actually pretty substantial. This section is what I was showing you, the travel time before, so you can see the effect of the fault. But now you look at it broadly, you will say, oh my God, this is really complicated. If you only look at this, how do you know this is a fault, not some shallow structures, right? Some other sedimentary basins. What we did was we take two cluster of earthquakes. One cluster of earthquake is along the fault. So when the wave comes to this section of the array, it's sampling either the northern side of the fault or sampling the southern side of the fault. And I have another cluster here showing in green. It traveled perpendicular to the cable, the fault, so that it samples the northern side more than the southern side. Only for the last section is sampling northern side. So now I'm comparing these two. Right? And you can see a lot of the variation outside, they're very similar. So now if I take the difference here, it tells you the contribution from the near fault but deeper structure to the north and south of the fault. And that's showing here at the purple line. And now you can see a very systematic difference between the two sides. So you have to correct all this shallow structure first, and then you can start to see this deeper structure. This difference here actually shows the contrast flipped. So at larger depths, seismogenic depths where the rays are turning, in this case, it's the southern side of the fault is actually faster. Okay. So Yehuda showed me his recent tomography, which seems to be consistent, at least at this spot of the fault.
Do you see these fault trapped waves for these gray earthquakes?
I'm not experienced enough to actually get a concrete answer. We tried that. It's a little bit hard for us to say, okay, one of the limitation of DAS is it's measuring strain. You were emphasizing it's not a seismometer. Strain is very sensitive to local heterogeneities. So when the P wave or S wave come into the array, all the local effect, scattered surface wave, makes the waveform very coherent but very complicated. So it's often hard for us to identify their fault zone head wave because they have pretty high speed and they don't show up as nicely on DAS. Yeah. So here is kind of our conceptual model, right? So at the shallow depths, either southern side is slower, northern side is faster, but at larger depths, it may be actually flipped. So this could be a tool we can apply more in the future to map different sections of the fault and see where you have this difference here. Okay, any more questions on this section? Yeah.
Are you planning on doing time dependence to look at near fault material geology?
Kind of under plan, but this is the next section. Okay. So, but I'm not talking about the fault. Yeah. Mostly it's hydrological was the most obvious one. We see a lot of, yeah, almost anywhere we look at, we feel like hydrology is just dominating. Temperature and hydrology are just dominating everything so far. We haven't been concretely, being confident about any deeper change. Yeah, the volcano is the next one we are trying. That may have some, deeper change that we can observe. Yeah. So just end on the fault zone detection part, I think the main strength of that in this domain is can capture this spurious arrival or scattered wave. So you can, figure out where they're actually coming from, right? Of course, we cannot do it for all the phases, but some of the major ones, which often come from faults, can be really studied in high resolution.
So how deep can you go with the fault detection?
The fault detection is on the order of hundreds of meters. The tomography travel time based, we can go down to 10 kilometers. But it's an average, right? So there's no super high resolution as a function of that. But on average, the
With your biomaterial, you showed that you can actually see deeper as well. So how deep can you see? Because this is
you mean the cartoon?
the cartoon, right? What's the
Yeah, there's no scale to this cartoon. The earthquake we were using has a turning depth around the 10 kilometer depth. So it's kind of average, from 5 to 10 kilometer. That was the most sensitive part. The shallow part we try to correct with NB noise tomography and the active source. We have to correct that before you can see. It's kind of like onions. You have to peel off before you actually see what's different underneath. There was a question from a student. Yeah.
I would like to go back to this spurious arrival you showed. Where in your simulations, when you put a scatter there, it's like symmetrically propagating both directions.
Yeah.
But in your data, you don't really see.
Right. Because when we were simulating this, we are simulating isotropic noise source. But the reality is not that. Like there is difference in the wave propagation distribution. Yeah. So yeah, we were not trying to capture all details of the.
Is it possible that there's a source there instead of a scatter?
Yes, we actually looked really deep into that question. Like was spending like 2 months struggling with that problem, right? Because there are some localized noise source. I was mentioning this pump. Turns out to be a big problem. It was not too far away from one of the fault we were looking at. So the pump could generate this. But in certain cases, we actually can see the coda part of it. Okay, so in this prediction here, if there is a scatter point, it causes spurious arrival. It's also part of the Green's function, and we can see both. Yeah, that was a not easy thing to rule out, but yep. Yes, it's possible. We assume all of these are surface waves, and we have good reason to believe that because they all show the same type of dispersion. Yeah, so if it's body wave scattered from below, we might not see that. Yeah. Great discussions. Okay, now let's look at the temperature change. I'm not going too much into the motivation. Marine and Shu Jian were already talked about. We'll talk about more about this. Idea is to take 2 stations, do the correlation, look at how it's changing over time, and then get a beautiful time series like this and correlate perfectly with other observations, right? It's very nice. So we were very inspired by this. We're like, we need to do this on DAS, okay? Rich crest, there's groundwater, it's a dry place. Can we see the same thing? And as I told you, we had the DAS already running right after the earthquake all the way until now. So, now you again looking at the noise correlation. What I'm going to do is take one of the traits here, and now I'm plotting every week's correlation, see how it's changing with time. So now it's 2019 July to 2024. Okay. So this is the acausal and the causal part of it. I think I don't need to do any more processing. You can see it, right? You can see this fluctuation here, and you can see the fluctuation here. One thing to emphasize that we are not using coda wave in this case, because we can already see them in the direct way. And we are confident this is a true change because they are perfectly symmetric. The 2 sides give you exactly the same response. That was the most convincing thing about Florence paper for Park field, that you showed the tilt of the DT on both sides. That's hard to change by changing the noise source, right? The same thing here, the 2 sides are very symmetric. So I can do this for any location here. I can look at how it's changing in space and time. So now I'm just jumping towards this one. This was a tomography model. Ignore that for a moment. Now this vertical axis is time. Horizontal is distance. Reference is the average. Okay. So when it's red, it means the seismic velocity was about 1.5% lower than the mean. When it's blue, it's 1.5% higher. So a few patterns you see. First of all, very clear seasonal patterns. Second, it's more red on top, more blue on the bottom, so there is a secular change. In general, it has been getting faster. If it's water related, it means it's getting drier, which actually makes perfect sense. This was the years of drought in Southern California, right? So it has been getting drier and drier overall. But you also see this kind of horizontal thin lines there. If I now plot the precipitation, you can see each one of them actually match exactly where you have those precipitations. Okay, so we're very excited about it. We're like, okay, now let's look at their, groundwater and everything. That's the figure. So now, I was showing this one here. You can do it for each frequency down to 2 hertz. Okay, so again, we're kind of limited by the bandwidth of the traffic noise, right? So this is the center frequency. We're going to be lower here, going to be higher there, right? So you can see it's observed over all frequency band. Something should already alarm you at this point. Yeah. We'll get to that very soon. Okay, all very good questions. Okay, one thing you realize is my high frequency, this is all in the same color bar. The high frequency looks a lot bigger, and the low frequency looks smaller. And we all know about the NB surface wave sensitivity kernel. High frequency is more focused on the shallow depths. Low frequency has a deeper sensitivity. The fact that the high frequency might show you a bigger signal is telling you it's shallow. And we actually know the groundwater in this region is about 75 meters. So what that means, if it's actually this change causing their DVOV, we would have seen bigger change on the low frequency part, smaller change on the high frequency. We see the opposite. So it actually has to be where the red is above the blue in the top, 20 meter or maybe even shallower than that. Okay, so that's the point we realize at least in this case, we're not looking at groundwater, we're looking at something else. Again, this is the time series, just the average over the array. Red is from higher frequency, blue is from lower frequency. Again, you see the seasonal and you see a slope there. So first, what is this big seasonal ones? It turns out it's just a temperature. It's a thermoelastic effect, right? The purple here is the actual temperature observation. You have to scale it and shift it to match this observation. And it's actually true that the lower frequencies, you have to shift it more because the diffusion effect of temperature takes longer. It's actually matching the observations. So you take the temperature and you correct it. This is what's left. Now in what's left, you get a slope here. And then you get all these sharp drops. Each one of the sharp drops coming from the precipitation. At the interval, we are observing this, which is 7 days. We don't see a phase shift. Okay, but the thermoelastic effect, see a very clear phase shift.
What's the size of the shift?
On the order of, I think the biggest one was like almost half a month on that order. I forgot the exact number. There is a change, frequency dependence, but on that order. Right. Yeah, there's a lot of uncertainty, like in those parameters, given the soil type. We choose some, arbitrary ones. It's on similar order, right? It's on the right order. Yeah. Okay, so now we know this is actually the long-term trend is the drought, basically, and the sharp ones are coming from their precipitation. So now we're going to do a little bit more modeling. So we tried our best. Okay, this is not going to be nice, but frequency dependence, you see bigger signals at higher frequencies, smaller signal at lower frequencies. That's the trend we need to fit. We take from hydrologists a guess what the subsurface water content is like, and then we start to add water over the top layer. Because we know there is precipitation, we add some water to the top layer. We use some soil mechanics model, say if you add this amount of water, make assumptions about the soil type and everything, then what's the velocity change? And then we were able to match that, right? So we're kind of tuning. We're tuning the water we add into the top layer, and we try to match this trend here. But we can do this for all the time we have, every week. So we now can get a time series, or based on that preliminary model, what has been the water content in this layer and how it has been changing over time based on our observations. And this is an inverted best fitting model. You can see there's a big band here. It's basically assuming end-member soil models, like either it's clay or coarse sand, right? So there could be huge variations, but this is the best we can do at the time. And then we ask the hydrologist, do you have anything that can benchmark me? Well, they don't. they don't have this type of observation. What they did is they take the precipitation, and there's a satellite measurement of the surface moisture. They do the best model they can, and that's what they got. Okay. I'm not sure you're convinced. I'm not 100% convinced by this, but that was the best we can do at the time. Okay, so it at least have a kind of qualitative fitting of the two. Yeah. Yeah, right. So in their models, when they run the model, they include their aquifer, but they're so dry that the water never actually get into the aquifer. Yeah, and we're not sensitive to that anyway. Yeah. To do that measurement. Yeah. Yeah. That's exactly the question we have. We have two approaches. One is we can dig a trench on Caltech campus, and we can make this measurement, and we think that's hard. So another approach, we go out where we are making this measurement, we wait a couple more months. And that's the second approach we take. So we decided that we are not satisfied by this. We bought some soil moisture sensor. We know it's coming from the top. We don't know how deep. We don't know how deep it is. Is top 10 meter, 20 meter, or top meter? We don't know. So we bought this cheap soil moisture sensors, $100 each. We buy like 10 of them. We go out there, push them to the ground. You push them to different depths. So some of them is pushed to maybe 20 centimeters. Some goes as much as 45 centimeters. So you can measure the soil moisture at all these different layers and then wait a couple months and see if we get the same result. So again, this is the one I was showing you. Now we are looking at this last window here where we have soil moisture sensors. Now I'm zooming in. This is a much smaller time scale now. This is less than 2 months of data when we have soil moisture sensors. We found that we actually can get a converged Green's function in 1 hour. So now we're going to do dV over V every hour near my sensor. So you actually can see these variations. So this is our measurement. This is measured dV over V as a function of time every hour near one of the sensors. So now you actually not only see the longer term trend, you see the daily trend, right? The seismic velocity is changing from day to night. Does this make sense? Well, the soil moisture sensor also have a local temperature sensor. So we know a lot of the temperature, we plot it on top of each other. They basically match exactly. That's the period where there's no precipitation. We say, okay, now we can get an empirical relation between the two. We calibrate it and we expand it. This would be the expected temperature effect. And we subtract from that, this is what you get. And then you look at the precipitation. That's exactly when they were raining. Okay? And I also have the soil moisture sensor data. I can now plot my seismic data, which is shown in black, with the soil moisture sensor data, averaged over the top 45 centimeters. And that basically matches exactly with each other. At this point, we know we're definitely measuring soil moisture, okay? And it's mostly very, very shallow things. We have one more proof that this is over even longer period. This is a pretty fresh result. This is to May. We take the different depth soil moisture data. There is a satellite measurement, which comes from the top 5 centimeters. We combine them together, get the red one, and then the black one is our observation, right? So we basically can use the top 50 centimeters of soil moisture measurement, explain almost all observations of our DORV in this case, after you remove the temperature effect. Mm-hmm. Oh, you mean not decaying? Okay. Yes. Actually, in this figure, it might be better showing. You actually can't, that was because that was a very narrow figure. Okay, if you extend it, you do see the decay of soil moisture, mostly due to evapotranspiration. And you do see that in the seismic data too. Okay, the decay. Yeah, it's just a time scale problem. If you look at a very short time scale, you don't see that yet. Over a longer time scale, you see the water leaving the system. We are still studying how much of it is the water leaving from the top, evapotranspiration, or how much is going below. We're still trying to finalize this last step here.
What happens when the blue crosses the green? The 40
Cross the green. This is because the percolation of water. The water is percolating down as a pulse. Unfortunately, we don't have the resolution to tell that from seismic alone, right? We see the average effect of the top 50 centimeters. Yeah.
Yes, so here you are looking at 7 hertz, so I suspect you are sensitive to deeper.
Yeah. Yeah.
And in the end, you have no time delay when you could expect still 1 because it takes some time.
Yeah.
Or at least maybe it's
I totally agree with you, right? But this is how, that was different from what's happening in nature, okay? So the water, yeah, at least in this location, this is not necessarily universal, okay? Because this is the semi-arid regions, very, very dry. The hydrologists tell us they are not expecting water to go below 2 meters. Like all water gets sucked in the top layer, and then it's dry, they all leave the system. So they are not necessarily surprised, but it's great to have actual measurement to show, this is the case. Okay, so one slide about why this is actually useful. Soil moisture turns out to be maybe as important as groundwater, because this is where vegetation directly get their water, from this top layer. So there has been satellite missions like SMAP and SMOS just dedicated to measure soil moisture. They measure soil moisture over a footprint about 30 kilometers, and then they measure what's happening in the top 5 centimeters, right? So in some sense, and they don't have a high repeatance time. So in some sense, like the seismic method get a very dense observation over a certain distance range and a continuous record with certain depth resolution. Not great, but some depth resolution is actually a very good news for them. And it's more scalable than pushing the soil moisture sensors. But based on my own experience, I would highly recommend to actually push a few sensors along the cable to know what's actually happening with the ground truth. Okay, I want to move to a very preliminary result. I only got this like last week, but I want to hear your feedback on this. This is for Iceland. This is a photo of one of the eruptions. There were beating walls, so the lava was diverted, but something still get to the town. So we think this is such an interesting event, we need to do something about it. So this is where the town is. Eruption is happening in this section. There was this cable going from airport for 100 kilometers passing across the town. So last November, I sent 2 students, put a DAS on it, turn this into a couple thousand sensors. So this is what the data looks like. Now you are looking at 10,000 sensors, 100 kilometer in 10 meter spacing. This is half an hour. Again, each one of these is one car driving on the road. This is one of those events, earthquakes, right? Propagating very fast. And this is what happens, what it looks like when the eruption is happening. Like there's a huge amount of seismicity, and you get all these earthquakes all the time, right? So we did a few other things on this topic, but I only choosing this part on the ambient noise measurement. So we basically do the same DVR measurement, but we look at the section right before the eruption and right after the eruption. So this is the one of the eruption. This is the time of the eruption. We take this part as a reference. So this is distance along the cable, right? So you can see before the eruption, not much is happening. Right after eruption, in the middle here, you get this big blue thing. Velocity is increasing, okay? And this section is only where the dike is. So when the cable pass over or near the dike, okay? Initially, we were not sure if this is real, but we got another one. We actually captured 4 total so far. And you get exactly the same pattern. It's very, very repeatable, different amplitude, but very similar patterns. Actually, you can see the effect of earthquake. This is essentially related to earthquakes. When you have too many earthquakes, we actually get a really bad measurement because it's not ambient noise. But it turns out the eruption in Iceland, this last few ones, is not always accompanied by not a lot of earthquakes. So very soon the earthquake die down, we can again get a very robust measurement. We actually can do this for many different frequencies. This is the 0.5 second period. So now you have channel pairs, right? So you have a starting channel, and you have all these other channels cross-correlating with it. And you see this blue band. So I'm trying to do spatial localization here. You see the blue here, you see a little bit red here. And then you can do an inversion on map view, because we are using direct waves. We're not using CODA. So we actually know exactly what the path is. So we can do tomography. We say, oh, this is the pattern of change you need to explain the observations. So you can see this is where the dike passes through. right over the dike, there's a velocity drop. And when you go to the side of the dike, the velocity is increasing after the eruption. And this is the fating, and you can go to some other frequencies, and you can see that it still have this dike here, big red patch here, and a big blue patch here. And you go to different frequencies, right? This is a longer period. So why is the velocity dropping along the dike but slightly increasing outside of the dike? What we think is happening is the dike intrusion process. This is now cross-section view. The dike is here. There's this deeper section of it. It's pressurizing. That's pushing the fault aside. So the color here is showing the stress change around the dike. So where you are pushing it apart, you see blue, where their fault are being the rocks are being compressed. So you are closing the cracks, and that's increasing the seismic velocity. But because the dike didn't propagate all the way to the surface, on the top here, you essentially have this grabbing effect, like you're pushing aside the crust is falling into the dike. And that's where you have the extensional stress. And when you have extension, you're producing small cracks, and you see seismic velocity drop. Actually, these are not small cracks. If you go out there and drive, there are cracks everywhere along the road. So it's not really surprising. But what this means is this transition from velocity drop to increase can actually tell us how deep was the dike intrusion. So far, our estimated value was actually pretty close to what the local geophysicist was talking about based on other measurements. So we're still trying to refine this result.
So here the scale is real.
This is real, yeah.
How do you get this resolution the way down?
This is the forward modeling. It's just a cartoon. It's a numerical cartoon. Yeah, it's a forward modeling. We're still trying to match this with the actual data. But this is our conceptual model. Yeah. Okay, I want to end this DVRV. This is the longest section. I want to end the DVRV section with this one example because we have some oceanographer friends here. I found this fascinating. We have this cable across the channel of Gibraltar. And when you look at the data, this is what the data looks like. A couple of kilometers towards the end of the cable and time. And you can see all these beautiful waves. But they're not seismic waves. They're propagating only at about 10 meters per second. So these are surface gravity waves, but the pressure effect you detect on the dust. You actually can convert this to frequency wave number domain. You actually can see most of them are landward propagating waves. There are some energy propagating in the other direction due to their reflections, right? And this is very shallow, hundreds of meters. It goes down to as deep as 500 meters, I believe, for Gibraltar. Yeah. And you can see there is a very asymmetric wave propagation here, right? So we actually did some ambient noise correlation. I think there was someone had a paper about what the theories you guys have been developing also applies to surface gravity wave field. I mean, it's wave equation, right? So we do ambient noise correlation. We actually got that. So this is taking one of the channels as a virtual source. This is 100 meter. And you actually can see the Green's function for surface gravity wave. So this is the Green's function as if you tossed a rock in the water, how the wave is propagating from that point. But you see only on one side because the wave is all propagating on one side. There's some energy on the other side, but it's very weak. But because we have this dense array, we can do something fancy. We take this FK diagram, we can filter it. We can separate the wave field into the land propagating part and the ocean propagating part. And I can cross-grade the two separately, right? So now I don't have the dominating effect of the landward wave. So the landward gets the same result as that one. I can also derive very clear energy on the ocean propagating part, which is great. But why this is useful? It turns out we can estimate this kind of image every hour, okay? So now I'm going to look at whether this surface gravity Green's function is changing every hour. And I look at them, this is what they look like, right? You can see the surface gravity wave have this very clear travel time change. And then on the negative side, on the causal side, you also see a little bit noisier. You can also see the change. The big tricky thing is their seismic velocity change, causal, acausal, they move symmetrically, right? They all go further away or further closer to each other. This one, they go together. That's not a velocity change. You don't actually expect water's dispersion to change. Okay, the gravity is not changing. This is actually due to the current. So the water is overall flowing. My cable is fixed on the sea floor. So it's a Doppler effect, right? So the water will get carried away by the tide. So once we know that, we actually can estimate the current velocity along the cable. And the two sides are basically matching each other. And we actually have a TPXO, a modeled current. Again, we're not also guard. This is the best we can find. The predicted one match it pretty well. There are some important difference. We believe this may be some other processes that's not in the model, like internal tides or other things that may be missed in this problem. Yep.
Is there also an effect of the tide itself, not the current, but the overall height of the water?
We estimate that that's too small for this effect. We can also measure, we can definitely measure that. The challenge is always it's a single profile. We'll get back to that problem in a moment. So, I don't know, oceanographer may care about this, may not. I heard that in some specific cases, have high resolution measurement, continuous record of current is actually important to them. What they do is they throw certain sensors down there, measure this current as a function of depth, but they don't have continuous measurement. So in certain cases, this might be a useful thing. But
This is the time associated with the time.
yes,
You see it 4 times a day?
you can see actually. Oh, I guess it's related to the gradient of the height, right? The movement is related to the gradient, so may have more oscillations. Yeah, I mean, there's an expert back there.
Any current you do a Doppler shift, you're actually measuring the total current.
Yes, we're measuring the total current projected along the profile of the cable. Yeah, and we can do it everywhere along the cable, every hour. That's what we can do. Yeah. Okay.
Does this also mean that your causal and causal results travel at different speeds?
Yeah, basically yes. Yeah, the one flowing together with the current looks a little bit faster. And that's how we confirm this is true. Yeah. Okay, I want to end it with this last section here on seismic noise generation. We have seen fantastic talk from our oceanographer friends here. I want to show this diagram again, right? We have all these models about how these seismic noise are generated and they are measured, try to map them globally or locally. But it's still relatively low resolution, right? Because our sensor is already on land, we try to infer what's happening in the ocean. So I want to focus on this particular case here using a very dense array measurement to figure out where the noise source actually is distributed. So this is the cable offshore Cascadia. So it's the OOI, Ocean Observatory Initiative cable. 2 cables. We were able to access this cable for 4 days. And one of them is shorter, one of them is longer, so I'm going to focus on the longer one. Here's the observation I will try to explain. Okay. It's the noise power spectral density. So basically, I'm going along the cable, measure the spectrum of the noise, how strong it is. And this is the observation. And you can see, okay, there is very shallow water, there is a surface gravity, where there are some other things happening. But in the most of it, you see this overall pattern, which is dominated by frequency dependence, right? Secondary microseism and other things happening. But you see a lot of detailed variations here, right? There's some stronger energy here. There may be some, variations in the energy levels. So what is causing this? Our first impression is, if all these waves are coming from far away, let's say from the deep ocean in the Pacific Ocean, they propagate in, they still will have this variation because of local amplification effect, sedimentary basins. But we know exactly how to do that. I hope I convince you I know how to do an ambient noise correlations. I can measure the dispersion. I can get a seismic velocity model. Okay, the seismic velocity model is, in the very top, we don't go to very high frequency, maybe problematic, but overall you see the variations in the velocity. And I now can take this velocity and I calculate if you have a wave coming from outside, what would be the amplification? And that's the bottom figure, right? Distance and the amplification depends on frequency. So you can already see quite a lot of variations, right? Where you have lower velocity here, like you can see a little bit bend, that means there's lower velocity there, is you get a little bit of amplification. And here you get a really low velocity near the top, you get some strong amplifications, which actually really match pretty well with some of the observations. So the red line here is one frequency's noise power spectral density. And the blue line is showing you the VS near the very top. So you can see where I have lower velocity, stronger amplification, I do see a stronger ambient noise spectrum, right? And you can see this other nice correlations locally everywhere. But that doesn't seem to be the whole story. If I look at a few different frequencies, let's say look at 0.5 hertz, you see that the correlation is very well. Anti-correlation of the two is very good. If you look at this 0.79 hertz frequency, you notice that there is still correlation, but it's not perfect. The blue line seems to overall going up, while the seismic velocity is on average flat. Notice that the blue line has a log scale. There's a big difference in amplitude, but the seismic velocity is not enough to explain all of it by amplification effect. So what this tells us is there is distribution of noise source, right? So maybe it's stronger here because the noise source is local, it's nearby, it's generating very strong noise amplitude. So how do we do that? How do we separate the effect of noise source and their side effect? Well, I really like this paper, right, in 2006. Very simple idea. If you have a homogeneous distribution of noise, the two sides are symmetric. But if the noise sources are coming from one side, then the two sides are different. But the amplitude ratio between the two tells you whether the noise are mostly coming from my left or mostly coming from my right. And it doesn't depend because this ratio has the same side of amplification at that point. So the side effect gets canceled out. So we're going to use this idea. If we come back to this ambient noise correlation now, so this is the correlation over this short section here with the middle point as the virtual source. And you can see this beautiful, right, X shape. But you notice the X shape is not exactly symmetric, right? These are the waves propagating landward. They're mostly long period. What that tells you is in the perspective of this section here, most of my long period noise is coming from my left towards my right. And the high frequency ones is oceanward. That tells you most of my high frequency noise is coming from my right. And we can make this measurement for a lot of pairs over the entire array, and we can form a matrix, right? So I have a source channel, receiver channel. Every point here is one cross correlation. I can measure the amplitude ratio of that. I have to use only a narrow section here because when we look at the pairs far away, I sometimes don't get good enough correlations, right? But within this band here, the color shows you whether the energy for a certain frequency is going landward or oceanward, the ratio. I now can take all this, if each frequency I can take the entire band, I can do an inversion. What's the distribution of noise source I need to have to quantitatively explain the variation here? Even before I show you the result, you should already be able to guess the result, right? The fact that all this low frequency one is almost all blue tells you it must be higher energy on the deeper ocean part of the cable. This one is red turned into kind of bluish, meaning that most of the source was actually distributed over this section, the shallow section of the cable. And that's, of course, what the inversion result showed, right? So this is different frequency. Between the two dashed line is where we have the best resolution. Outside, when near the end, it's harder to constrain. right? So you can see the low frequency has higher energy towards that end. But unfortunately, I don't know if this is just like that or just mostly coming from the deep ocean. I lack resolution there. The same thing happened here. But you can start to see the variation you actually need for the distribution. More interesting on the high frequency part. 0.3 hertz, you see this peak in the middle of the array. Most of their energy was actually distributed at that point, around that point. And you go to higher and higher frequency, this peak starts to shift towards the land into shallower and shallower water. Okay? So now, I have shown you two different things. One is I do ambient noise correlation. I get the travel time, velocity. I get the site amplification effect. Based on the amplitude ratios, I gave you the source distribution. Now I'm going to multiply these two together, and I give you this figure on top. This is our expected noise power spectral density based on the source distribution and the local amplification effect as a function of frequency. This is the observed ones. This might look different from the first figure you saw, but I removed the mean frequency dependence, which is, every frequency has different noise amplitude, right? So I take out of the mean of that frequency dependence, and this is what it looks like. I'm actually pretty happy about the comparison here. It captures a lot of the features, right? Some of these amplifications in this frequency band, we kind of see the same shape here. There is a big amplification here. We see the overall amplification in the region, but just not as localized. And that was not surprising to us because this high frequency part of the amplification care about very shallow structures, and we do not have really high resolution for the top layer. So it could be even narrower, or our inversion is damped for the amplitude ratios, so it could be sharper than this, but overall we are capturing all of that. So in this particular example here, we think we actually can almost fully explain in low resolution the full ambient noise spectrum here. Part of it is coming from noise source distribution, part of it is from the site amplification, right? For example, if you look at 0.2 hertz, the blue is the actual observation, right? The orange line here is coming from the site effect, and in this case, the source is making no difference. It's not a big contribution factor because most of them are coming from the left and far away. If we look at a higher frequency, you see the observation, and the blue one, the orange one here is a site effect. It probably should have been stronger, but most of the contribution is actually coming from this pattern of the red line, which is the source is being distributed closer to the array, right? So we are capturing a lot of it. I think for this part, it's really exciting that we are looking at the in situ observation. It's a limited distance, but it's an in situ observation of how noise is being generated, as it's being generated and as it's being amplified along the path. So if we can have more of this, right, like multiple arrays or a certain area, and then be able to take oceanography models, either from wave models or like SWOT type observation we saw earlier this week, if we can actually match them, that would really show we actually understand, at least in this section of it, how these processes work. Right? And that's the current missing link. I would need a graduate student to work on that. Okay, so come back to these slides here. I hope I have convinced you this, in this big context, going towards a lot more sensors of reasonable quality, right? Because of the scalability and the density of sensor and the continuous operation, right, of these sensors, it really is presenting a big opportunity for ambient noise seismology. It might not be surprising at this point, right? Ambient noise seismology is all about turning sensors into virtual sources. And now that always scale is n squared, right? And now we have a lot more sensors. We just can do this a lot better. And you can track the wave field, and you're going to learn a lot more from the ambient noise field, right? So that's really the take-home message here. I want to end with the slides of advertisement to this conference Zach Spica and I are organizing in Vancouver. Officially, the deadline already passed, but there are still ways I can get you in there. So I totally encourage you to come. We get a not as good a representation from European countries. We want to have a more international discussion at this conference. I hope some of you can attend this conference. Yep. Thank you so much.